Hey, so let's start class. So I guess the homework was not due if you didn't hear on Monday. We extended it until Saturday, and I didn't want to do midnight. So I had to do it at 11:59 p.m. just so there's no ambiguity. Hopefully that's okay with everyone. So it's due. It's due this Saturday, so you can enjoy Friday and Saturday night doing homework for my class. So the other things to mention, there's a quiz, which is going to be next week on Monday in class. I expect you all to come. If you don't take the quiz, you're not going to get points for the quiz. So you should come for that. And then I'm actually probably going to be traveling next week. So the TAs will be here to proctor the quiz. And then on Wednesday, we're going to have a lecture that was a normally scheduled lecture on doing this approximate versions of the stuff with the matrices, so approximate PCA and versions like this. And so my grad student Mina Goswami is going to give the lecture. So this is actually her area of research, so she knows this area very well. So she'll be a very competent person to give the lecture. But she'll be lecturing on Wednesday, so I'll probably be traveling. So just a reminder, the intermediate report is then due the Monday after break. So there's some discussion of this on the big project handout. So take a look at this. If you have questions, send me emails. Basically, I want you to show that you've made some progress towards a goal. It doesn't need to be a lot, but just so you kind of can see if what you're doing looks like it's going to work, or if you need to if it's not going to work, then this is kind of your last chance to really, you can say, we tried this and it's not working, we're going to try and reboot this. This will be kind of your last kind of time where you can really kind of make a change. So I just want to kind of make sure you're making good progress toward this so I can give you feedback on the best way to conclude your project. But that's due Monday after break. So that's still a few weeks off, but make sure you don't forget to do that. Okay, so then so then the lecture today is going to be on it's going to be on the singular value decomposition and its applications. So how many people have heard of the singular value decomposition? So a few of you. Okay, how many people have heard of PCA, principal component analysis? Okay, so most the same. So there are several kind of applications, and under the hood, what they're really doing is the singular value decomposition or something kind of that's similar. So if you've heard of PCA, well, it's basically the singular value decomposition. This is after this is after you do something called centering on the data. Then you do the SVD and you get the PCA, and we'll explain what this is. There's also stuff we talked about before, the eigenvalues and the eigenvectors. So this would be the eigen decomposition, of a data set or a matrix, and this is very related to the singular value decomposition as well. But we'll talk about this difference, and then another thing called that's called MDS. So this is multi-dimensional scaling, and so multi-dimensional scaling as words, I don't think really makes sense. Like principal component analysis, this will explain what those words mean. Multi-dimensional scaling, it was called this because I think like in the 1930s in the psychology literature, someone made up this term. But the idea here is singular value decomposition starts out with some data points and kind of tells you some important information. MDS starts with all the pairwise distances between data points without actually knowing what the data points are. And then you're kind of doing the same thing. Okay, so to understand all of these, I think the kind of the most intuitive way is to start with the singular value decomposition, understand what's going on here, and then we can each of these different applications in this context. This is, I think, the singular value decomposition carries the most intuition of what's going on. So we'll focus on this. Okay, and so what this is doing is the way I like to think about it. So if you take like a class in linear algebra, you'll think of this like a matrix, and we'll talk about this as a matrix. But I think of this as you have a point set in high dimensions. Okay, so the number of dimensions is going to be equal to d, and so then the number of points is going to be equal to n. And so then we're going to see how this will give rise to an n by d matrix. Okay, and so then what the singular value decomposition is doing is it is going to do this dimensionality reduction. So often the problem is in high dimensions is sometimes this is hard to deal with. We talked about searching for nearest neighbors in high dimensions and how this was really tricky. So what you want to do is take these points in a high dimension and you want to take these down to a smaller dimension. And let's call this k. So a smaller dimension k. So maybe d is something like 100 or 1,000, and maybe k is, maybe it's 2, so you can draw pictures, you can put all the points, you can draw them. Maybe it's 10, and then you can start using certain algorithms. The smaller the dimension, you're losing information, right? It was in high dimensions for a reason, probably. But it turns out in a lot of cases, you don't lose too much information when you do this. And the singular value decomposition gives you a way of doing this that in some ways is the best possible way. It's optimal in a certain sense, and we'll explain precisely what these are. So we're really doing this dimensionality reduction in this optimal way. So it's hard to draw pictures of this. So let me think you have this data that looks like this, and so what I can say is this data lies in a two-dimensional space. Think of the x1 dimension and the x2 dimension, or x and y if you want. And then what the singular value decomposition is doing is it's trying to find a line, and it turns out that for the SVD it has to go through the origin. For PCA it does not. Okay, but for the SVD it has to go through the origin, and you want to find this line so that the distance of all these points onto this line. So again, these are the residuals. So I want to take each of these. So if this is a point P, then this distance here is RP, right? And so I want to minimize the sum over P of RP squared. Okay, and now for when we talked about doing linear regression on Monday, it was a vertical distance. It was only in this x2 coordinate. Now there's no notion of which coordinate I'm measuring. I'm saying it's just the closest point. So from this point x, I find the closest point. So from a point here, from a point P, I find the closest point on the red line. I don't have to be restricted to moving vertically up and down. Okay, and so this singular value decomposition is finding this line that best fits this data. So this is going from d equals 1. So this is an example going from d equals 1 to, d equals 2 to k equals 1. It's hard to draw things higher than that. So, but in general, you can have this k dimension being, so if d is like 100 or 1,000, then you can say, well, I don't just care about a line. I care about, say, maybe I want K to be 10, a 10-dimensional space. So then, not just a line, I have this 10-dimensional space that goes through the origin here. And I need to kind of worry about this. And then I can still define the closest distance from a point onto here, and I can still optimize this. And again, to actually implement this yourself, you probably don't want to do it. This is built into MATLAB, and actually, what's built into MATLAB is this old code that's written in Fortran, and most programming languages have a library you can install that can do the SVD, and it calls the same code that's in MATLAB. Now, there's some differences. There are some cases, like if the data is sparse or if the dimensions are weird, that you'd want to calculate it one way or the other, and MATLAB is kind of actually really carefully profiles the matrix and tells you which way to do effectively, where some of the other languages just call the basic one, and sometimes it doesn't work as well. So sometimes it's better to do it in MATLAB than to call it in even someplace like Python. Sometimes it'll be more robust, but most times it's exactly the same. Okay, so there's this operation to calculate the SVD, and it will give you this kind of low-dimensional space that and kind of how the data points live in this low-dimensional space. Okay, so this is kind of abstract. This is a picture. Let's go and look at what the SVD does, and we'll break down the components, and we'll kind of see how it gives you this low-dimensional space, okay? But this is the picture we're going to be working towards throughout the lecture. All right, any kind of questions now before we start breaking this down? Okay. But this is a lecture that if you haven't thought about these high-dimensional data, it can be kind of confusing to keep all this stuff straight. So don't hesitate to stop and ask. Okay, so the input, yep.
So we talked about, okay, so for that example, the dimensionality was 2, we're going to reduce it down to 1.
Yeah.
Now, do we get to specify what reduction we want it to go down to?
Yeah, so actually what you end up doing is, you call the SVD, it gives you all choices of K between 1 and D, the original thing, and then you can just take as many of them as you want. And it actually tells you how much information each additional dimension is giving you as part of this decomposition.
Okay, so that was...
Yeah, so you have to choose this still. This is just like in clustering. There's this value K. What is the right value K? I don't know. You can kind of plot how much you're getting with each dimension and kind of say, well, this one, it starts to not be worth it anymore. Or maybe you say, I want 2 because I want to draw a picture. I want to draw all my data points on the piece of paper. And I can only do that with 2 or maybe 3 with some kind of visualization software where you can move them around. So sometimes you say, so it's got to be 2 or 3. Sometimes you say, well, I look at how much I'm capturing with my data, and maybe 10 is a good number. Yeah. Okay. All right, so we're going to start with, I'll write this over here. So we're going to start with, we're going to think of having this matrix A, which is, it's going to be n by d. And we'll think of this as n is equal to the number of points, and d is equal to the number of these dimensions. Okay, and so then I'll draw this picture bigger here, but just as a reference. You're going to have, so this length here is n, and this length is d, and going across here is going to be one of the, this is one of the data points. Okay, so it's going to have these d different coordinates in here. Each of these is a coordinate, and I start in this big d dimension, so I have d columns in this matrix. And so this is one of my data points, and I have n of these going up and down here. Okay, and so then what we're going to do is we're going to say that, so what you call this in MATLAB is, you call SVD of a matrix A. Right? So you store your data in this matrix A, and then you call this command SVD. It gives you 3 matrices U, S, and V. Okay, if you call it this way, it'll give you them, load them into these it'll load them into these three variables. Okay, and so kind of I think the right way to think about this is that you have some data, and so typically, I think I like to think of where n is often larger than d, so it's a tall matrix. So this would be A, so your matrix here. And so you're going to get three matrices out of here. The first one is going to be U, and you'll see why I draw them like this in a little bit. This one is going to be, this is S. And so this one is going to be V transpose. Okay, so you got V here, but the reason why this is because you're going to have the property that A is going to be equal to the matrix U times the matrix S times the matrix V transpose. Yeah?
Just so I have the overall picture, this is basically just for feature selection, right? So, or can it be considered that? Because, I mean, obviously we can encode our features as zeros and ones and as a vector and whatnot, but
yeah.
Does that really apply to
Well, so feature selection is kind of, so often people say feature selection, they're thinking each of the D columns is one of the features, and you want to say pick a subset of the columns which are telling you the most about the data.
Is that
right? Well, so this will tell you something about that. We'll get into a technique. I think Mina will talk about this next week in the approximate version briefly. That's called like the leverage scores of the columns, and these kind of tell you how important each column is towards that. There's kind of some tricky things because you could have two columns which are both really important, but they're telling you exactly the same thing. So do you take both of them, or do you only take one of them? Which one do you take? Feature selection itself is kind of, I think it's not, I don't think it's a well-resolved area, and maybe that's because there may not always be a great way of doing it. This is going to tell you which kind of, it's going to kind of give you linear combinations of the columns. So it's not going to tell you just one column to pick, but it's going to say, combine these columns, all these columns magically together as some super column, and this is the best single super column you could take, and then we'll give you another one that'll be completely orthogonal to it, that'll also be a linear combination, and we'll keep doing this. So I'll explain that a little bit more as we kind of go through this development. But yeah, so it's good to keep in mind, and if I don't answer that anymore, ask me that again. Okay, so it gives me these three matrices, and so this U is going to be n by n. This one is going to be this is D, and this length here. This length here has to be n. Needs to match the dimensions of A here. This is n by D. So this is again n. This is n by D is S, and this one is D by D. And so S is going to have the property that it's going to only have information here on this diagonal. Everything here is going to be all zeros. So you can ignore everything except for on these points here on this diagonal. And so especially what's interesting is that the stuff down below here is all zeros. So that means that anything you multiply in this part of this U matrix, you have D things here and then you have n minus D here, this stuff doesn't really matter either. Because you're multiplying it by something that is zeros over here. So this stuff is not important, but it's often given to you as this n by n matrix. And the rows will kind of nicely, I think each of the rows is going to be each row is going to be a unit vector, but then the parts over here doesn't matter anyways. The columns of both U and V, so the columns of U and V are also unit vectors. So each column here and each column of V, which is a row of V transpose, so these are unit vectors, and these are the right, in V it's called the right singular vector. And so we'll call this V1, V2, and these are, so V1, V2, up to VD. And so in U, these here are called the left singular vectors. Okay, and so these we'll call U1, U2, up to UD, and they actually go up to UN, right? But after D, they stop mattering. This part is inconsequential. Okay? So, and then these values in here are called the singular values. Okay? And so often these are called, sometimes they use a sigma in here, but these are called S1, S2, up to SD. Okay, so I only need to store just a single list of vectors here, and then these I store these full columns. These are of length n, these are of length d. So these are d-dimensional vectors, these are n-dimensional vectors with the u. Okay. The other property is that these both u and v are orthogonal matrices, which means that their columns are going to be orthogonal to each other. So that means if you take the dot product, let's say for matrix V, the right singular vectors between any Vi and Vj, for I not equal to j, then this is always going to be 0. So if I drew this as Vi, then Vj is going to be a right angle. Okay? So these are always going to be right angles with each other, and you can think of they're in higher dimensional space, so they can all be orthogonal to each other. Right? And so you think, can they all be orthogonal? Well, if you're in a d-dimensional space, the original coordinate axes are all orthogonal to each other. So this makes sense. I can fit exactly, if I'm in RD, I can fit exactly D orthogonal vectors. I can't fit any more, but I can fit exactly up to D. And so these are not necessarily, and are usually not, the original axes. They're a different set of, a different set of these orthogonal vectors. And these are telling me information about the data. Okay, and then, so these are telling me something about what direction the data is going in. And these singular values are telling me how important those directions are. So often what's done, and in MATLAB what's done, is that these values, Si through Sd, are sorted. So you have the property that Si is greater or equal to Si plus 1 for all values I. So the largest one is S1. So S1 is the largest. This is the top singular vector. Okay, and this is telling you about something about the kind of the most, and this first singular vector corresponds with this top singular value. This corresponds with the top singular vector, V1. So this singular value tells me how important this singular vector is. So it tells me how important the right singular vector is, or the first one, or the first left singular vector. Okay? All right, so now hopefully maybe you can kind of jump to some conclusions, and you're starting to think, maybe how does this affect high dimensional data? Right? So these are kind of the, one more thing I'll mention about these orthogonal matrices that we'll need a bit later is that that the transpose is the inverse. So V transpose is equal to V inverse. So that means that the identity matrix you can get by doing V transpose, or V transpose V, right? So these are both equal to the identity matrix. Okay. Okay. So now, how do I take this data encoded in here, and if I thought of these as data points, then tell me about this dimensionality reduction approach, right? So So one nice picture I kind of like to draw to think about these matrices is, well, okay, so I'll preview, I'll tell you, so how do you do this dimensionality reduction? Well, these singular values are decreasing in order of importance. So what you're going to say, if I want a k-dimensional singular value dimensionality reduction, I take the top k. So I'm going to take only this part, and then I basically just set these other ones equal to 0. And then that means I just take these top k directions up here, so I set some value k, and I take the top k of these things here, and then I kind of ignore the rest. And this what's left over is going to tell me about the dimensionality reduction of the points. So these data over here, and I'll repeat this on a fresh slide because this is getting too busy, but this is going to tell me this new subspace Rk. This is going to give me a new k-dimensional basis describing the points. This is going to tell me how much each of those directions is important, how much data is along each of these directions and in the singular values. And then the left singular vectors are going to tell me the actual coordinates of the points in this new space Rk. So for one of the data points here, it used to be a d-dimensional vector. Now I only go up to k, and these values multiplied by the singular values ends up giving me the coordinates in the k-dimensional space. Okay. So this is kind of busy. So let's kind of go and break this down a little bit. And let's kind of go. I've got an example in the notes, but I'll come back to that at a time. Well, let me kind of show you a pictorial thing of what's going on here. So if I think of some data set originally, so let's think of a data set again that's in, so I've got n points in D equals two dimensions here. And so I can draw them in 2 dimensions. And so then this corresponds with a matrix A, and I'll say a matrix A in red here. And so one way of thinking about a matrix is I can think about doing some operation where I do AX. So I take a vector, this will be a 2-dimensional vector, and let's say that we restrict that this is a unit vector. So if a unit vector is telling us something about is telling us information about a direction. So unit vector means that the vector lies, it's a point that lies on a circle in R2. So this is telling me some direction. So this is a direction x. And so if I evaluate the norm of AX, so I'm multiplying x times A, it's a 2-dimension by an n by d, n by 2 matrix. It's telling me a norm, and the norm is then, so basically this is going to be equal to the sum over all of the data points, 1 through n, of AI x squared square root. Okay, so this will give me a vector, and it turns out the norm is going to be equal to this. It's the dot product of AI with x. And there's this nice way I can draw a picture to represent this. So it's going to be, this A is going to exactly be, and this A corresponds to this ellipse that's centered at the origin. Okay, it's centered at the origin, and if I look at this vector x, and I take this out until where it hits A, this distance from the origin is going to be exactly AX. So a matrix is kind of telling you, when you're looking at the norm, it's telling you conditions about this ellipse that lies in here. Okay, and if you know the mathematics of an ellipse, it's specifically defined by some basis. So you have some set of orthogonal directions, and so these directions must be orthogonal to each other, and they have a length to them. This defines the ellipse. And it turns out that the longest direction is the first, is going to be the first singular vector. Actually, this is the first singular vector times the first singular value, is this first direction. And the second direction here is going to be v2 times s1. So remember, v1 was a unit vector, so it actually lived on this circle as well. And v2 is also a unit vector, so it was orthogonal. And then the s told me how far to go out. So the data, this ellipse is saying this data kind of lies, the shape of the data is kind of this elliptical shape, or I'm modeling it like an ellipse. If I model it like an ellipse, that's kind of what taking the norm of the matrix is doing. And it's telling me how it's spread out in this way. Right? So if you think of it, an ellipse, if it was really long and skinny instead, if the ellipse happened to be very long and skinny, that would mean, because it's defined by these data points, that all the data would kind of lie in here. And so that means that if I took a one-dimensional subspace along here, I'm capturing most of the variation of the data. And so if I just took the subspace where the ellipse is not too skinny, that's what I'm capturing with taking the top k of these singular vectors and these singular values. These are this interpretation it's the right singular vectors. Right, so I'm taking those, and how do I know how skinny it is? Well, the skinniness is told by the singular values. The values S1 through SD telling me how skinny it is. So if it gets skinny enough that there's not a lot of variation here, I don't need to take this direction. So I can kind of go back, do the singular value decomposition, look at these singular values, and when these start to get too small, I just set them out to 0. And what that's doing is it's looking at this data and saying, I don't care about these other dimensions. I don't care about these directions going this way. There's not enough information there for me to care about. Okay. All right, so if you remember, so let's kind of explain this basis again. I said that, I guess it was this slide here. Great. So I said that a times x I could write this way. I could write ai times x for any data points here. So it turns out x, originally x was in x1, x2, up to xd. It was this d-dimensional vector. It turns out for any d-dimensional vector, I can rewrite it exactly as the sum equals I1 to d of some alpha I times vi. Right? So I can use the right singular vectors here to rewrite any vector x. This is because this is a orthogonal an orthogonal basis. Right? So if I originally have points, let's use this picture here because it's more clean. So I have x1 and x2 dimensions. So actually, these are actually the dimensions. But I have this data point. Let's say it lies right here. So its coordinates are 3, 1. Now, if I want to write it in terms of, remember I had this unit circle here, and I have these v1 is here, v1, and this is v2. Now I can write the same data point in these coordinates. So now I can say that the alpha 1 is going to be projecting it onto v1, and I look at this length here, and let's say that this is 2.5, and alpha 2 is going to be projecting it here, and now this becomes negative, so maybe this is minus 1. So turns out, let's say this is 3, because this is just a rotation. The length of this vector shouldn't change. 3 and minus 1. So yeah, I guess that's possible, right? Or maybe it's 2.5 and this is So this needs to be a little bit larger, so maybe this is like 1.3 something something. I don't know. But the point is, I can now write this vector in this new coordinate system. In the new coordinate system based on this vector, this basis v, the new coordinates are alpha 1 and alpha 2. So now I can represent the same data point using these new coordinate system. So that this right singular vector is v is saying, instead of using my original coordinate system I wrote the data in, there's a better coordinate system. It works just the same way mathematically as the original way I stored the data, but this one is nice somehow in that it's capturing this ellipse property. This first direction, the most data is ascribed. If you're only to pick one direction to describe the data, the first coordinate tells you the most about the data. If you were to pick two directions that are orthogonal to describe the data, the first two directions are the best ways to do that. Right? So this is automatically coming out of doing the SVD. You're getting all this information. Okay, and if you go back, then so in order to get these values alpha I, what you can do is you do vi dot product x. This turns out this exactly gives you this distance. If you do the dot product, if you remember the dot product, this is equal to say the sum. I used I here, so let's use a j equals 1 to d of vi. So that the jth coordinate of this vector times the jth coordinate of the vector of x. Right? And this is just the dot product. This gives me this value a, alpha. Yeah?
Were you not losing any information from reducing the dimensionality?
So, when you choose, if you used all d of the right singular vectors, you aren't losing any information. There's some maybe kind of precision issues, but these libraries do a really good job. It's a really small amount of precision that's lost. Now, if you choose a set of these vectors that is not all d of them, you only choose 2 of them, then you are losing information. Right? So I'm saying this. I don't know this data point except that if I just chose 1, I'm just saying I know it lies right here in this direction, but I don't know how far off in this direction it lies. So I've lost that information. But it's kind of saying, if you were to pick a direction, this is how I can overall lose the least information. All right, so okay, so what people will do is they will say that if I go back and look at this picture and I take the top k here, the k values here, these values are called UK is going to be the top k of the left singular vectors. SK is going to be the diagonal matrix with S1 up to SK, and VK is going to be V1, V2, all of these, the first K of these vectors. And then people will write AK is going to be UK times SK times VK transpose. Okay, so people write this AK, and what this is often called the this is a rank K approximation of A. So I take the original data A, and it's a rank K matrix. So what does it mean to be a rank K matrix? People heard of rank of a matrix before? Okay, so it has this linear algebraic thing that if you kind of solve for various properties and so forth, and geometrically it means all the data points lie on some k-dimensional subspace. Is what's going on. Or if you took, in another form, if you took the SVD of this rank K matrix, only K of the singular values will be non-zero. The rest of them will be 0. Okay, but this matrix A sub k is going to look just like the matrix A. It's going to be an n by d matrix. You're going to have all the data points still in the original coordinate system, but they're going to be restricted to lie on some subspace. So this point here would have been replaced with another data point here. But now I'm still giving it its original coordinates. So that's what's in A sub k. If I just want the new coordinates, then I just do sk times vk transpose. That's basically the new coordinate system. And now this sk times vk transpose is only going to be, that's telling me the new, let's see, if I just do, if I do uk times sk transpose, this tells me the data points in the new coordinate system. It'll give me an n by k matrix. If I just do, this part will be an n by k matrix, and so it'll give me the points in the new coordinate system. Whereas this part, so vk tells me the basis that the coordinate system lies in, and it tells me how important each of those coordinates is. Okay, so all, if you're doing basic dimensionality reduction, it's all lies inside of this SVD decomposition, which is kind of built into the software. So if you have high dimensional data, often the first thing you might think of in analyzing it, if it's kind of too big to understand, is take the SVD and look at the underlying structure. Okay, so what are, let me mention, what are some, so let's define precisely these optimality conditions about A sub k, right? So let's look at A sub k, which is this uk times sk times vk transpose. So this is going to be, so I can use A sub k to kind of precisely say how good this approximation is, what some properties about it. So I can, one way of looking at it is I can do something like, it's the same dimensions as A, so I can do A minus AK. I can subtract these matrices, and then I can take some norm of the matrix. So this, so if I put an F down here, this is known as the Frobenius norm, and this is basically, I do I equals 1 to n, and j equals 1 to d, and I look at all of these entries, aij minus ak ij, and I look at the difference and I square them. So the squared Frobenius norm is defined this. It's the sum of all the differences between the entries. I square those differences and I add them up across the whole matrix. Okay, and so if I restrict to, and if I care about, I want this to be small, I want these to be as close as possible, this is the best, this is the best rank K matrix in terms of minimizing this error. Okay, so, and it turns out if I look at the singular value decomposition, I can actually write this more simply. This is actually the same thing as I equals k plus 1 up to d of si squared. So if I just look at these singular values and I square the ones from k plus 1 up to d, so I skip the first k of them, then these si, and I take these and square them, then this is the same thing as this error here. Okay, so this tells me the kind of the amount of information, the sum of the squared information that I'm missing, and I want that to be as small as possible. And so this is the best way of doing that. There's another thing where this is optimal. If I look at A minus AK, and I look at the spectral norm, so let's not write squared here, so don't need to. So if I look at the 2 norm of a matrix, we talked about the 2 norm of a vector. 2 norm of a matrix, or the spectral norm, is defined a little differently. It's the max over all x of A minus AK here times X. So I can multiply it by a d-dimensional vector again. And so I can either restrict that to a unit vector, or I can divide by the norm of this vector. So this is the spectral norm. What this is saying is that if I go back to this picture here, there's some direction where I'm measuring the air. That's what this AX is doing. I'm measuring the direction of this ellipse. And I want to say, and I want to look instead of at A at the difference between A and A sub K. And I want to say, over all directions, let's find the maximum direction that this is. So the maximum direction of this ellipse. And so if it's a unit vector, then this bottom part is 1. So I just want to maximize this. That's my error of the part that's left over. And it turns out that this is going to be precisely S of K plus 1. Right? So this makes sense. I had this ellipse picture here, right, for describing A. And the first direction, this was V1. The second direction was V2. And so I kept taking the direction giving me the most information. And those are going to match exactly. A and A sub K in these directions are going to have no error. So the X in those directions would be 0. But X, if I just took V1, then the X in the V2 direction is going to be the next thing as large as possible. And so the length of that is going to be exactly this K plus 1 singular value. So that's what's the spectral norm. It's saying what's the worst error I can do by multiplying an X by this matrix. And if you can do a left multiply again, and it's still then instead of using the right singular vectors for this picture, you're in n-dimensional space using the left singular vectors. But you still get, the value is still the K plus 1 singular value. So it's still the same bound if you're left multiplying instead of right multiplying. And for matrices, this matters a little bit. So this tells me that, so I'm minimizing this in the matrix. So let's let's remember what this means, right? Remember if I did AX, if I looked at this was again the sum, it was I1 to n of the dot product of AIX squared. Right, so I've taken each of these data points, I project it onto X. This dot product is the length of the projection, and I square it. And so that's what this norm is doing. And so I can take the square root if I want, but I'm minimizing it so it's still true if I squared all of these things here. So if I'm minimizing this, that means for any direction X, I want to minimize the sum of these dot products, the sums of the length of the projection. That means that if I look at all of the data points here, right, they lie like this, and I'm looking at their residual cost of projecting them along some direction X onto this one line or this subspace that I've collected, and I look at the one direction where this cost in terms of that direction is the most, and that is what I'm minimizing. So in any direction, I'm saying the sum of the residuals in that direction is as small as possible if I only took a k-dimensional subspace. And if I looked at the total lengths, it's hard to see because this is now in higher dimensions, but I've looked at the total lengths of those projections, of the things that I've missed by taking the k-dimensional subspace. That's going to be this Frobenius norm. So this is in any one direction the total amount of error of all the points projection, the total sum of residuals squared. And this is the sum of residuals to the closest point on the k-dimensional subspace. Because again, the distance is this. I can break down the square distance using the Pythagorean theorem into the sum of these orthogonal parts, and that's exactly what this is telling me. Right? So what the SVD is optimizing is for any subspace that goes through the origin here, I want to minimize the sum of the residuals of the points projected onto that subspace. The sum of those squared. Okay? And so this is automatically given, right? So just like in the ordinary least squares regression, there's this way of automatically calculating this optimal thing for minimize sum of the squared distances. It turns out, again, the SVD is doing that. We get this automatically by just running this algorithm. Okay, so for the one of the homeworks after break, you're going to have to run this on some data and look at it and kind of see how well it does. It's pretty easy to do. You just run it. I recommend using MATLAB, or if you don't want to pay for MATLAB, you can use Octave, which is open source, or you can do it in R. You just run this. You'll see this decomposition. You can kind of measure how well it's doing. It's very simple to use. The tricky part is understanding what it actually means, right? And so that's what I'm trying to convey in this lecture. Like, what's going on? You're finding the subspace that's describing your data. Yeah.
All CADE machines have MATLAB.
Okay, the CADE machines at MATLAB, great, yeah. So it's on there. I know some people like to use their own laptops. You can download Octave. People haven't had too much problems using that. Sometimes it's a little buggy, but for what I'm asking you to do, it should be fine. Yeah.
So I'm still not sure what these two equations, what they mean in the grand scheme of things. What do they accomplish?
Okay, yeah. So what do these two equations mean, right? So I guess there's a couple ways of looking at it. One is the actual kind of just look at the calculations, right? You're summing. This is saying. So first thing is to realize you're picking this matrix which is ranked K, and that means it's describing a K-dimensional subspace, right?
This is what SVD is doing?
So the SVD gives you the full decomposition, and then you just take the top K vectors and singular values.
We choose a K, and we perform those operations.
Right, so you choose K, you reconstruct this. You don't need to reconstruct it, you can just use the parts that tell you the information. But if you were to reconstruct it, and that's everything that you have left about your data, but you restricted it lies on a K-dimensional subspace, then if you measured error in these ways, you can't do any better. Okay, so if you restrict to a K-dimensional subspace, then under these measures you can't do better. And these measures are intuitively saying the sum of the distance from the original point to the new position of it squared, right? Or if you pick any direction and look at the sum of all the movement along that direction squared, both of those you're doing the best possible you could do for a K-dimensional subspace. Yeah.
So both these are kind of a measure of how much information you're losing?
Exactly. That's right. That's right. Yeah. So how much information you're losing by reducing this dimension of this data, right? Okay. So
Question.
yeah.
So if we're talking about that, then obviously, so in A matrix K, or rank K,
Yeah.
if K is equal to D, our error should be 0, correct? Then,
Correct.
okay,
Yeah.
so then as we go down, as we increase K, then our error should increase. But are there times where our error does not increase? Because maybe that particular piece of data wasn't important.
Yeah. So it's to interpret that, it's really useful to look at these ways of looking at this error, right? So I'm looking at this for the Frobenius norm, which is the sum of all the distances squared. I'm looking at the sum of all the singular values squared that I threw away. And I'm just looking at the largest one I threw away. Okay, so as I'm increasing K, if the data already lied on a d-dimensional on a d-1 dimensional subspace, then the last singular value is already going to be 0. It already has to be 0 by the definition of what they mean. So that time I don't lose anything. But they're in sorted order, right? Remember, I have this property that Si is greater or equal to Si I plus 1 here. So every time I do another one, I'm losing more information than the previous step I took. So typically, what happens in most data, and later on in class we'll talk about kind of these sort of distributions, but I can look at plotting these i's, and this goes from 1 up to d, and this is Si squared. And often it's going to kind of look like this, where actually this is going to be closer to 0. Let me see if I can try drawing this again. So it's going to be come down, and then it's going to kind of get pretty close to 0. There's really not going to be a lot of information after some point, and you can set k to be equal here, either when you start actually getting useful information. Right? And if this is the square, then if you sum under this, right, actually if you sum under this side, that's what you've lost with this Frobenius norm. The sum of all these squared states. So you look at this volume we've lost. And most of the information is in the top ones here. And usually it decays pretty sharply. So there's some work where people look at these ways you can generate data randomly, but it makes sense for certain data problems. And in almost, unless you do something really structured, it is always kind of decaying. There's always some way you can fit some subspace through there. And typically what it means is that there is some actual phenomenon that's actually describing your data, and then there's other stuff out here which is kind of noise. The stuff you're chopping off is often the noise in the data, and the real structure is in this part up here. So it's, you're usually losing stuff, but that stuff usually didn't tell you anything in the first place. So most data in high dimensions actually has lower dimensional structure to it. And so that's why doing this is so useful, right? Even if I had instead I'd cut off here, I still maybe, if I just take the first, if this went up to, say, 1,000, maybe I take the first 10 of these, and this volume under here is still 90%. I still maybe get 90% of the information of a 1,000-dimensional space with only 10 dimensions. Sometimes it's better. Sometimes you can do that with 2 or 3 dimensions. Sometimes it takes more. You have to kind of look at these plots to know. But this is a kind of a really useful kind of tool for doing this. Okay, so let's talk about the relation of SVD to some of these other operations we've talked about, to the PCA, to the eigenvalue decomposition, and to this MDS. Okay, so PCA. So often, when people just call the SVD and call the result just PCA. PCA, the idea is I want to get these principal these principal directions and these principal values. And so that's a set of directions that says these directions tell me how much information are the most important directions in describing my data, and these principal values are telling me how important those directions are. And often people will just say these are the right singular vectors and these are the singular values. That's usually not, there's often, there's different nomenclature for these things. I think most standardly that's not the best way to do it. Kind of the idea is the SVD is modeling your data as being centrally symmetric about the origin, where your data may actually live something like this. So if your data lied like this, then SVD is going to model it saying that the first direction is like this and the second one is here. So if I just describe my data in this direction, I'm not really capturing the information well. Whereas if instead I said, well, let's pretend that I can draw my directions from inside of here and draw it like this, then I get a much better understanding of my data. I don't need to restrict that these go through the origin. So this is not restricted to go through the origin. So I can often, most times, data, if you think of things like, if you look at your dimensions is like the weather. Every day in the last month, I recorded the maximum temperature. They're usually not centered around 0, right? There's it was some was a crazy month, and it kind of was decreasing, but the maximum temperature was always above zero. It was between 70 and 30 or something like that, right? So that means that in my dimensions, the SVD model is going through the origin, and I don't want to do that. I want to model it as having some other points in the center. So what PCA is going to be, you first center the data, and this goes from A, and we'll call this to CNA. So this is the centered version of A. This is maybe A tilde, and then you run the SVD on A tilde, and you take the principal directions are going to be the right singular vectors, and the principal values telling you how important they are just going to be this singular values. Okay, so yeah.
Could you help me understand a little bit more of a practical example of somebody using SVD as analysis?
Yeah.
Because on just like a set of data, just so I can understand how, on what particular set of data would this be useful?
Right. So this is actually this point's kind of tricky. A lot of people will use it when you shouldn't use it. So you should not. So let me first tell you what you should not do. You should not have like customer data and you have like the height and the weight and the income and the age as those being your dimensions. This is wrong because you're treating all of the units of all your dimensions the same in PCA or SVD when you should not be doing that. They should all have the same units. So I saw a talk recently where people are looking at this example of weather, and they said, let's look at these trends in weather, and let's look at the temperature every day, the high temperature every day of the year. And so I have D then was equal to 365, and you have to be careful about leap years and whatnot. And so then I have every year I have a D-dimensional vector, a 365-dimensional vector, and I have a bunch of n years of data. And now I want to understand trends in this. So I want to find some trends in this data. And I find these linear trends that are kind of going through this data. And this was a way of kind of fitting this data to a lower dimensional subspace that you can analyze. Now, often, you might say, well, these trends may be kind of curvy, and the temperature doesn't always increase over time. But if you have if you have a polynomial that's a bounded degree, it must lie in a low dimensional subspace. The degree of it restricts the how high of a dimensional subspace it can lie in. So if you have a polynomial in high dimension that fits the data, there's a low dimensional subspace slightly higher than the degree of the polynomial and of itself that will also capture the same data. So you can reduce it and then do polynomial analysis. Or there are other tricks you can do with the lifting, like I showed before with the linear regression, that you can use to fit that. People use this stuff for not just weather, but analyzing the stock market instead. Right? So these stock markets, you have a price of the stock every day, and maybe now every day is a data point, and the dimension are the different stocks. So now you want to understand the trends between these different classes of stocks. Right? So as one goes up, another one goes down. They have an inverse relationship. So if you want to balance your portfolio, you want to find some stocks that have inverse relation with each other. And so you find when one goes up, the other one goes down, then your portfolio kind of follows the market and is not as more stable. And so you can find these basic relationships in this lower dimensional space. Yeah.
And so with the stock example, like the first K dimensions would be like the K most important stocks that determine whether the market is.
Well, it's like linear combinations of stocks, right? It's not one stock. So think of it like you have a fund of stocks that is a mixture of these stocks, and you say this first dimension tells me if I had the most variable fund possible with the most instability, then I would pick this fund. That'd probably be a horrible fund unless you were a very risky person. I don't know that much about this portfolio analysis, but I know people use it as a starting point for a lot of these sorts of things.
Eigenfaces is kind of a cool one.
Yeah. So there's this other thing where this called eigenfaces, where they take these images, and so what they did is they took a bunch of mugshots of people, so all the faces were aligned, and you can use these other, like these SIFT vectors features we talked about earlier, but you can just use the pixels of the image, and you treat each pixel value as one of the dimensions. So then you want to reduce the faces down to a very small number of dimensions. So then you can classify. So one way is you take a bunch of pictures of some person under different lighting conditions or way they're moving or different hairstyles, and do the SVD, the principal component analysis of that, and that tells all the ways they can move is some small subspace. Then you get another person, you take a picture of them, and you see whether they fit into that subspace or not. And that kind of tells you whether they're kind of a similar person. But it turns out for these images, which have thousands of pixels when they first did this, you can do it much more pixels now, but you only needed like 40 dimensions to really describe almost all the variability in these faces. So this was using kind of these principal component analysis. Or they were doing eigen decompositions, I think, but it's really the same thing. Okay, yeah.
So you mentioned the SVD can be applied only to the dimensions with equal units. What do you do if the dimensions are equal units?
So if they're different units. Yeah. So then what you should do is you figure one dimension that you really want to measure, and you do and then you should do something like linear regression instead. Doing dimensionality reduction is dangerous because you're treating all the dimensions equally, and you don't know which one is more important towards actually doing the prediction, which is what the linear regression is doing. If they're all different coordinates, then it doesn't make sense to do dimensionality reduction anyways. You shouldn't be taking linear combinations of these things. That's a really good question, though. So, only apply this in these settings where everything is the same units. Okay. So let me quickly just cover, how do you do the centering? How would you center a matrix? So what you want is that, so this point becomes the origin. You want to take all of these data points and translate them. So now it looks like this. I don't want to rotate them at all. I just want to move them. So now what was, I think, is my center is now the center here. And basically what you do is you take all of the, so to do the centering, so if I want to, you can do each axis individually. So just for the first coordinate, you kind of take the average value. So this is similar to what we talked about in the linear regression. I could say this, my data set was P, and I do this Px for the first coordinate, and I take the sum over P in Px, and I do P1, which is the first coordinate. I sum all these up and I divide by n. So this is the average x coordinate. So the average x coordinate is going to fall to be a point about here. So this is the average x coordinate. This is the average y coordinate. And then for every data point, I subtract off this average x coordinate. All right, so I subtract off this. And so there's, I wrote this here as this centering can be done as a matrix. There's a way people like to write this in matrix notation when they do linear algebra stuff. You can do it as the identity matrix, the n by n-dimensional identity matrix times 1 by n times this is the all ones vector and all ones vector transpose. So this is n by n all ones matrix. And so the identity minus the the n by n 1 over n matrix. And it turns out if you set this equal to this matrix Cn, which is n by n, you pre-multiply A by this, it does this centering. It creates a centered data set. So you can do this all in linear algebra if you wanted to. So you first multiply by the centering, or you compute the averages and subtract the points, and then you run SVD, and this gives you the singular vectors. They aren't because I didn't rotate the data set. They still point in the exact same directions here. So if I get this vector here and this one here, it's the same here. Now it might be useful to also keep track of this center point, but you don't necessarily need to. I just know the variation along these directions, perhaps. So SVD is kind of like if you did SVD and you kept one extra dimension, you should be able to capture everything you did with PCA. But it's giving you, it's not telling you which direction is really the most important. So if you center, it's telling you much better description of what's going on in your data than if you're not centering. You get these red vectors, which aren't really aligned the right way. Yeah?
What was 1 over n?
Well, n is the number of data points. So again, n is the number of data points, d is the number of dimensions. So yeah. Okay, so this is PCA. So PCA is kind of often the term people use for analysis, where SVD is the linear algebra operation. And if you're doing this for analysis, you should probably center the data first. It'll give you a better description of what's going on. Yeah.
What are the ones?
These are all 1 vectors. So this is an n by 1 vector, that every entry is 1. And so if I multiply 1 by this 1 vector by 1 vector transpose, I get an all ones matrix that's n by n. And I divide each of those by n, so it, I don't know. So if you work it out, it ends up, it's doing the same thing as calculating the mean along every direction, subtracting it. And actually, this should look kind of like the Laplacian. It's not exactly the same thing, but this maybe gives you some intuition of why, when we looked at this unnormalized Laplacian, it was doing something kind of like this to our data in a graph. It's kind of constructing some kind of normalized way of looking at it. It's a similar structure here. Okay, so this was PCA. So what? Remember, I also talked about these eigenvectors. So we talked about in spectral clustering, where you converted your graph into a matrix, into a specific thing called the Laplacian matrix, and then you found the eigenvectors of this, and the first eigenvector told you how to draw those vertices of the graph on one line, so that you could cut them into 2 parts, right? So this was this eigen decomposition, and it had, if you have a matrix M, so this is a matrix, and so if you go, if there's some vector that equals lambda v, so then if this happens where you can multiply a vector by the matrix and you get back a scalar times that same vector, then this vector is called the eigenvector, and this is called the eigenvalue. So then this is the eigenvalue, and this is the eigenvector. So it turns out if there's a matrix and it's of rank R, then there are R distinct eigenvectors and eigenvalues. So this works only with the matrix if this matrix is square. So we can't do an eigendecomposition of an n by d matrix if n is not equal to d. This matrix had to be something like n by n, or it has to be d by d. So what is the relation between these eigendecompositions? So what I can do is I can create a set of eigenvectors and eigenvalues, right? So what is that relation to the SVD? Well, it turns out that they're really the same structure, but you have to convert your matrix A into some square matrix. Okay, so if I write down A transpose A times V, and these are the eigenvectors of A transpose A. This is now going to be this is now going to be a D by D matrix. I've made it square by multiplying it by itself, and then I multiply by these V, which are the eigenvectors. So, well, I can write out this decomposition. A transpose, I can use this SVD decomposition, V S U transpose. So, and if you take the transpose of S, which is a diagonal matrix, it doesn't do anything. So I'll leave this there. Times V S. Oh, sorry. This should be a U V transpose. Times V here. Right. Well, what I can see is that I remember that U transpose is the inverse of U. So if I did this multiplication across U transpose times U, this disappears. So this becomes V S squared V transpose V. And again, this V transpose V is going to cancel. So this becomes V S squared. So these were this was the diagonal matrix that with the singular values. And if you square a diagonal matrix, you multiply it by itself, all it does is it squares all the entries on the diagonal. Okay? So, and what I've gotten is I've gotten these vectors back. So if this was my matrix M here, and I multiplied by these vectors, this is a scalar, so I can switch it over to here. So I've gotten back my vectors. These, and this V, this worked if this was the right singular vectors. So the right singular vectors of A transpose A, of A, are the eigenvectors of A transpose A. So the singular vectors are the eigenvectors if you turn the matrix into a square matrix. And the eigenvalues are the squared singular values. Okay? But there are two ways of turning a matrix square. I can also do A transpose. So this creates an n by n matrix. And then if I do the same trick with a U instead here, I'm going to get U S V transpose V S U transpose U. And now the V and the V transpose here cancel, and I get U S squared U transpose U, which is U S squared again. So if I translate this into an n by n matrix by doing A transpose, then the left singular vectors are the eigenvectors. And again, the squared singular values are the eigenvalues. Okay, so they're the same kind of structural object, but it's just after you've converted the matrix. So this one is often called the covariance matrix. This is the covariance matrix of A, and this is called the Gram matrix. So if you're doing kind of kernel methods in machine learning, I don't know if you're going to get to that in the machine learning class, then you often just look at this Gram matrix of a data set. And so if you just have this Gram matrix, and by n it's telling all the pairwise relationships between the points. So you often will just look at this, and the eigenvalues of an eigen decomposition of this is the singular value decomposition of A, the original data set. Okay, so I'm running out of time, so let me just quickly tell you multidimensional scaling. So this MDS, this often, and so there are actually many forms of this. I have a paper at some point where I made up a new version of this, but there's something called classical MDS. So the classical way, what it's doing is it takes a matrix D, which is n by n, and this stores the distance between all pairs of points. So each entry, the ith dij equals, say, the distance between point I and point J. Okay? And the goal, you're just given the distances. You're not given the data points. You just have something that told you these distances. You want to put these points into a low-dimensional space. You want to create points that try and preserve these distances. Okay? And so often people are vague about what they mean by trying to preserve the distances. And you can try and explicitly do that, and there are ways to do that. But classical MDS is a way of using this eigendecomposition to do this. These are distances. You want to convert these into the dot products. You want to convert this into a similarity matrix M, which is going to be n by n. But each entry, so the ith j entry is going to be pi dot pj. And it turns out you can get from the distances to this dot product by kind of looking at what the squared distance means. And there's a way to convert it. And then these dot products, this mj, where these are the dot products, is exactly this Gram matrix. So you turn it into this similarity matrix from the distance matrix, and then you do the eigendecomposition on here, and you take the first two eigenvectors, the top two eigenvectors, which are the top two singular vectors, and use those to represent the points in 2 dimensions. So this is what classical MDS is doing. There are other versions, but this is kind of the most heavily used version. And so this goes back to like psychology literature in the 1930s or something like that. People were already doing this sort of stuff. Okay, so all right. So quiz will be on Monday. Be on up through the frequent item stuff. I think if you've looked at the homeworks, and if you've understood the stuff in there, then the quiz shouldn't be too hard. Hopefully, most people will finish in the well before the end of class. I don't intend to be hard, but so hopefully it'll be good. But you have to be here to take it. So.
Hey, quick question. So this is the CDF I got from KD++.
Okay. Yeah. It looks kind of reasonable for 20 points. If you did more, it would become smoother, and you'd probably see a plateau.